Yeah, we can go. Okay, our next topic is industrial control systems by Marin and Dejan Strbad, who will also at the end give some info about the SCADA ICS hacking challenge. So without any further ado, I'll let themselves introduce themselves better than I can. So hit it.
Hi all, so I'm Marin from Kraken and Ascalia and a few other projects. In any case, my background is electrical engineer, system automation. I spent some time working on underwater vehicles, designing the underwater drones, but that was like 8 years ago. In the meantime, I went into the IT sphere, mainly distributed systems, data acquisition, data processing, etc. And over the last 2 years, we've also been working on Ascalia, which is an industrial system for monitoring, alerting, etc. Dejan might want to introduce himself. Okay, Dejan is a physics student major, and we started Kraken long time ago, actually, like 5 years ago this month, and he is the main brain behind all DevOps related stuff and in general architecture, designing systems, etc. So, as I said, at Kraken we do mostly distributed systems, so purely IT. We've been doing marketing systems, data aggregation, analytics, machine learning, etc. for clients like Care4, Forbes, Nestle US, Nestle Mexico, etc. And we are the technical team behind the one startup that's called Next User, where we do those things. Other than that, we also provide consulting services to big international clients when they need to scale their systems or when their business becomes big enough that they need to optimize their performance. On the other side, recently we started another company called Ascalia Limited, based in London, which is a result, let's call it a spin-out from Kraken, where we did aforementioned industrial monitoring and analytics platform. So, what are industrial control systems? Industrial control systems are exactly what it says. They're control systems in industry. So they are not supposed to break down anytime. They are the ones that make sure that your lumber mill, that your factory, that your car factory, they all run smoothly 24/7. And being such systems, their inherent description of them is that they're closed. So factory is an isolated system which is closed from the outside world until now. So that was the case so far. But as we know, everyone is opening up. Now everyone is talking about IoT, blockchain in industry, and other buzzwords. And what started to happen is these facilities, industrial facilities, if you call them like that, they started to be exposed to the outside world. And that's a nice field of play for hackers all over the world. And you can every now and then read about nuclear power plant being hacked, about exposing vulnerabilities, etc. Why is that? That's because of their very slow adaptation to new technologies. So let's first describe a little industrial control systems and what they comprise of. So industrial control systems usually comprise of some end actuator, some end thing that does some useful work. That can be in a lumber mill, that can be a lot of motors that move lumber around and chop it up or saw it, etc. Or it can be pumps. So for example, a lot of people don't know that actually every city is full of pumps underground, which pump the water and keep the constant pressure. And they're all actually industrial control systems because they are little engines that run pumps which are controlled by some smart or less smart computer which makes sure that the pressure is always on. Other part is this smart computer system. So it's usually PLCs. PLC stands for Programmable Logic Controller, which is extremely dumbed down computer. They're usually simple microcontrollers. At least they were until recent times. They are very dumbly programmed using what's called a ladder diagram. So that your average Joe from a factory can modify applications. It has input, it has output, very simple. If, then, turn off, turn on, etc. On top of all that, sometimes you can encounter SCADA. SCADA is system control and administration platform. Originally, I believe, developed by Siemens or someone like that, or ABB, which is a proprietary system for controlling such systems. And its use is to be able to remotely or on-site, more often on-site, control complex systems. For example, every industrial facility like chemical plant, Pliva, Vindia here, they all have some form of SCADA. It's a central panel where the engineers that are on call can see everything that's happening. I don't know, in Vindia, okay, this is the level of milk, now this amount of sugar is added, measuring those things, they can modify it remotely, etc. And we have other passive elements, but that's not worth mentioning. So, about the PLC. So, as I said, it's very dumbed down. It's like 8-bit microcontroller or 16-bit microcontroller, but it's not a computer. It's not something that you can SSH into. It's not something that you can that connects to a VPN or anything like that. It doesn't have an OS, nothing. It's literally it's comprised of some bootloader, which takes an application, always just one application, which is compiled on a PC and sent there, and then it's executed in a loop, and that's all. It just runs this in the loop. So this, when you program it, it's a ladder diagram. It's called like that because it looks like a ladder. It starts on the top, goes down, and then again. Very dumb. And the joke is that it's very expensive. It's very expensive because it's supposed to run always. You're not supposed to have any downtime. It's very expensive to have a downtime, especially if there's no one there. If you have a field that's watered 24/7 and there's no one nearby, if something goes wrong, it's a problem. If you have medicine being built, being made, and for some reason one sensor goes off or something's wrong in the application, suddenly the drugs will be bad. So they're very expensive. At the same time, they're very vulnerable and they're very simple. And additionally, connecting to them is usually very old school. On one side you have like serial interface, which we all know. A bit more complex interface, which is run on a physical layer of serial interface, is Modbus. Modbus is, I believe, 35 or so years old, and it's still used everywhere. There are like newer versions of this Modbus protocol, like Modbus over Ethernet, but the protocol is the same, just the physical layer changed. So it's a bit more reliable and a bit faster, but still it's pretty dumb. And then you have some proprietary protocols like Profinet, Fieldbus, etc., but they're closed protocols. When they're closed protocols, it means that if you go to Siemens, you can get your PLCs with Profinet. You will pay one PLC, for example, 1,000 euros or more. It's usually more in terms of Siemens, ABB, etc. You will pay more, but the thing is that thing can only interface with its own machinery. So you cannot get a Chinese engine or Chinese frequency converter talking to this because the protocol is closed so that it cannot talk to each other. And then people revert back to Modbus. This is one example of a PLC. They look pretty much like big, ugly boxes. This one is very advanced because it has a screen. Usually they don't have anything. Sometimes 7-segment screen. So, but PLC is just a controller. So, as I said, it runs a program which runs in a loop and does something. What does it do? In the most simple case, we can describe a sawmill, for example. So what does sawmill do? When someone puts a log on the conveyor belt, it needs to detect that there's a log on the conveyor belt, and it needs to guide it through the entire sawmill, and on the outside, you get a plank. And this is done with the PLC. So PLC is connected to a sensor which detects, oh yeah, here's a log. I will turn on the conveyor belt. once the log comes to the end of the conveyor belt, another sensor will trigger and say, aha, okay, it's now here. Now I need to turn it left and turn on the saw, for example. That's the simplified version. And just does that constantly. And then people who work at the sawmill, they just need to put on the logs, and that's it. That's their only job. And outside, someone needs to pick them up. And they all boil down to this. But PLC is a logic controller. So it works on, I don't know, 230 volts, but it doesn't actually connect to an engine or similar machinery. It connects to what's called a frequency converter. Frequency converter is another form of control system in industry, which is used as intermediary between control and the end actuator, which is an engine of any kind. It doesn't matter. Why is it called frequency converter? Because now we're going into field of control systems in industry, but to simplify it, you have an engine which runs on power, on volts and on electricity. And in order to have it run either at constant speed or constant torque, etc., there are different algorithms how you achieve this. Mostly used with AC motors is frequency control. So what the PLC says to the frequency converter, it tells him, okay, I want you to run at 60% of power, and then the PLC just conveys that information to the frequency converter, which then in turn calculates what needs to be the frequency based on some parameters, etc. So they're the intermediary, they're the actual people, the actual devices that do the work. And they're everywhere, they're literally everywhere. If you go to a shopping mall, all those huge fans and AC, like air conditioning, AC, they all have some form of frequency converter in them, some form of logic controller. Well, truth be told, ACs don't have PLCs, unless they're some industrial big units, but they always have some form of logic controller. And they're literally everywhere. So some form of frequency converter goes with almost every engine, other than your father's sawmill at his home. And they look pretty much the same like the PLC. Difference between PLC and frequency converter is there is no loading direct applications into a frequency converter. They come preloaded with some applications, with some firmware, which allows you to do basic control. So you can program your frequency converter and tell him, okay, I want on this exit, on this so digital exit, digital output, I want you to just detect if something is there or not. And then I want you to, on this output, I want you to control this engine at this constant speed, and that's it. Very dumbed down. Where's the problem? Trick is in the fact that they also connect to the same protocols like Modbus, Profinet, etc. And if you connect them to the outside world, everyone has access. These devices have absolutely no form of access control, any whatsoever. It doesn't matter what the protocol, they don't simply have it. If you can plug a wire into it, you can control it. And the only form of access control, for example, in a frequency converter is you cannot tell it to go faster or slower unless you first write number 1 or like 1 bit into a certain register. And that's all. So it's no username, password, there's no encryption, nothing. You just need to be really sure, and they ensure that by saying, okay, first say I'm really sure on this register, and then tell whatever speed you want. Problem is, you can see it if someone bad gets access to this in a sawmill, suddenly your saw is not running at 50%, but it's running at 120, and I don't know, people get chopped or something. So it's bad. And that's entirely possible, especially today when everyone is doing IoT, everyone is doing IoT, like industrial IoT. Problem is they usually do it like, oh, I bought an Arduino and Modbus is basically just bumped up serial protocol. I'll just connect it, I'll call that IoT, and I want over-the-air updates, so I will expose it to the entire world. And then you have people like Tonimir who will be like, whee! Let's play. Let's find them. And that's entirely possible. Modbus works on a single backbone, so you can connect any number of these devices onto a single backbone, connect one IoT device, and you can control all of them together, not at the same time. It's a very stupid protocol. If you have multiple devices, you need to say, hey, device 1, do this, and then device 1 does that and tells you back. Others need to ignore, so it's very old school. Further on, SCADA, the next level is the control and acquisition part, which usually looks something like this. So again, you have to realize that the end users of all these systems are not programmers. They're very rarely highly educated people. They're usually people who know their job. If I'm working at Pliva, I am usually a chemical engineer. And all I need to know is what's going on. I don't need to understand how is it working. So these SCADA systems usually look like this. They're a visual representation of the actual system, very often with drawings to make it like very simple for anyone. And they just display different information in different places. I don't know, you have a tank, there are valves, what's the pressure, where does something go, etc. They've been around for a very long time also, pretty much since early PCs, and they didn't evolve much. And again, they're very, very vulnerable, which wasn't a problem so far because, again, these industrial facilities were closed-off systems. So no internet access, no nothing. You have a control room, you control it. Now they started to expose these things to the internet. You have a lot of solutions that say that they're SCADA for the next century, etc. But there's always this problem of security. And that's the main challenge in industrial control systems in general, security. As I said, today everyone is doing some form of IoT, and they don't care too much about security. And in case of, I don't know, Philips Hue light bulbs, okay, someone can hack it, but so what? He will turn on and off your lights. It's not so critical. But if someone can hack your hospital or your AC system in a hospital, then that's a problem. And additional problem is this vendor locking. So you can be aware of problems in protocols, but it's very, very hard to get them changed. Modbus exists since '82, so no one will ever change it. It is what it is. It's very slow, it's very shitty, it's very painful to work with it, but no one will ever update it, and it's everywhere. If you have any small facility, they all run on Modbus. Also, how do these systems connect to these SCADA systems? It's exactly through those either very old or very closed protocols, which makes the whole system very unscalable. For example, some of you will be working for a few days hacking our system, but also one of the challenges will be to hack simply directly the frequency converter, which will not be connected to a SAW. And it will be from Emerson. It's a low-budget frequency converter, relatively cheap in comparison to ABB, with very limited set of functionalities. And that means that it's off-the-shelf available, it's currently used, it's up-to-date device in terms of industry, but it only has serial connection and Modbus, nothing else. And how they connect? You get a little module which you connect to to each of the elements of your control system and hook them up to SCADA. Hence, it's not scalable because for each piece of equipment you have in your, sorry. Yeah.
Question of Modbus implementation. Is there a specification that all behave like the specification?
Yeah, so that's another problem. Yeah, so on one side you have closed protocols that are like, okay, at least they're always fine. But problem with Modbus is that everyone has their own interpretation. For example, you download Modbus datasheet, and this will be one of your challenges. You download Modbus datasheet, or you download some off-the-shelf library with Modbus, and you try to hook it up to something that you know that it's on Modbus, and it doesn't work. It simply doesn't work. Like 2 years ago when we started to work on Ascalia, I was the one writing the first firmware for our devices, and I did just that. Okay, I have Modbus. It's very dumb. I did the hardware interface to make it work with the higher voltages, opto isolation, and okay, in theory it should work. It doesn't work. I get mumbo jumbo, I see something's happening, but something's wrong. And then you need to start debugging the protocol to figure out what's wrong. And then you realize that, okay, so they added one bit because blah, I don't know why. But they simply add something. Modbus is very timing sensitive. So Modbus doesn't work on 10-meter wire, at least not good, or not at least on a very thin wire. So it's very timing sensitive. If my device says, on the bus, it says, hey, device 1, please tell me what's the current voltage. Everyone hears it, and just device 1 needs to reply. But it works like, hey, it's like I'm saying, I don't know, Alexander, what's today's day? And then I start, 1, 2, 3. He didn't reply, fuck him. And then he replies, I ignore him. But the problem is, if I ignore him now, and at the same time I start speaking on the same bus, boom, no one will hear me, I will not hear him, it goes to shit. And that was the, for example, problem.
Bus arbitration like in CAN bus?
No, CAN bus is a much better protocol. It's still open and shitty and everything, but at least it works over long distances, it works reliably. This one is very specific. And yeah, the main problem is that every manufacturer makes their own variations. So I tried pushing my changes to one of the open source libraries for Modbus to make it work with this specific device, but the maintainer just said, I have a bunch of these, so just have a fork and that's it, because everyone has their own interpretation. Sometimes it's bigger, sometimes it's smaller, but it's always a problem. So, security, yeah. US CERT body also is saying that it's one of the big challenges, like the recent incident with the nuclear power plants and their vulnerabilities. It's a big challenge now, the security aspect of IoT. And no one really cares about your fridge, but they do care about your hospital, your shopping center, your sawmill, etc. And that is really a problem, and there are exploits popping up every day. So it's very important to have a secure version of IoT for industry. And that's how and why we came up with the Scalia. Originally it started by Emerson partner reaching out to us, hey guys, distributed, would you be able to do something like SCADA but cheaper or better? And then we came up with what is today this. So we have a central cloud-based solution, blah, it can be on premises, typical SaaS stuff. On the left, you can see our devices that we have, our own devices. So one of them is the one that's used as a gateway to various types of industrial control systems. So that's up there, so PLC, real-time units, frequency converters, whatever, different sensors. It can connect also to different types of protocols. So currently we support Modbus, Zigbee, XBee, CAN bus, normal serial interface, etc. And we have some part with the monitoring vehicles, but that's less interesting at this point. On the other side, the Scalia collects all this data, aggregates it, processes it, and it gives you a modern SCADA. It gives you modern interface, which some of you will compare with Grafana, very modular dashboards, etc. But more importantly, it gives you predictive maintenance, real-time analysis, and real-time alerting and alarming, which is the first point why they even reached out to us, which was real-time alerting and monitoring. What's the problem? As I mentioned, people who work in these facilities, they're usually not engineers. So if you're a company from Zagreb and you install an industrial control system for a client in Dubrovnik, and he has something that needs to run 24/7 and suddenly it doesn't work, he will call you and he will tell you, hey, nothing works. You can try via telephone, figure out what doesn't work, but it's very difficult. Oh, check this relay, or maybe this circuit is wrong, or maybe some sensor is not working, maybe some floater is stuck. It's difficult. And then you need to send someone from Zagreb down to Dubrovnik to check out what's wrong. And then he's like, oh shit, okay, now we need to go back to Zagreb and get one of the million possible things that could have been. So you are wasting money. So money gets blown away simply because of this long problems. And that's why we built this. So you can remotely get information from all the parts of your industrial control system. You cannot modify them remotely. That's one thing that we developed, but it's not deployed. It doesn't know. At the moment, we are not so certain in our security capabilities to allow someone remotely change parameters on this machinery. That's too risky. That's why we're here. That's why you are here. That's why you are here to hack it and to help us find vulnerabilities so we can make this thing better. We also have in pipeline with some companies and with Tony adding on top of all of this our solution like TPM and some other modern ways of making it more secure. Okay, this we basically described. So far we're working with this directly with Emerson. We're working with a potential client in France who has an oil refinery who needs a system like this. We are working with Odašiljači i veze on some projects. Definitely there is a big need for such stuff in the market, but pretty much no one cares about how it looks. They all ask about security and they ask about modularity and interoperability. No one wants to update their systems, and that's an important part of this ADS thingy. ADS stands for Ascalia Drone something, I don't know, system. Sorry, my internet went. What is it? Yeah, so they all care about not having to update their own equipment. Like everyone can connect to SCADA, everyone can go to Siemens, buy a SCADA solution, or someone else buy a SCADA solution and just replace everything they have. But they don't want to do that. They have a system which has been working on the same hardware for the last 10 years, literally. Why should they spend 10, 20, 30,000 euros on upgrading their system just so they can remotely see it? They don't see entirely the value. Sometimes there is a value of that, but still, people are very, very reluctant to replacing everything they have. So a few advantages that I already mentioned, basically. So no vendor lock-in. We support pretty much a lot of protocols. Mostly we add them as prospective clients, request them, and then we start a pilot, and that's how the process goes. We designed it basically with security in mind. So the whole thing about connecting to these devices, sending it to the internet, collecting it, there isn't much innovation to be done there. It's all pretty simple. It's data, you grab data, you send data, you process, you store. It's nothing special. But we are trying to make it secure, and that's why we wanted to participate and sponsor this event. And the idea is to make it secure and to make a new version of SCADA, to make a SCADA for the next, well, for this century.
Does it run on a toaster?
No, but toasters are not our target market. Our target market is things that matter. Actually, theoretically, I mean, you can ask later Alexander, the bald guy there. Maybe it runs on a toaster. He's the one who's writing the new firmware. If it has NetBSD, then it will work. So, about the workshop later this week. There will be 2 challenges, and there will be 2 systems in the lab downstairs. First one is like a vendor system. We took one of frequency converter, one of the many that we work with, connected it to BeagleBone, and put on our software. And sorry, I'm talking about a different one. So this is a frequency converter connected to an ordinary BeagleBone. You will get access to this BeagleBone, SSH, whatever. And your job will be to access the frequency converter, change its parameters, stop it, whatever. You can consider it some kind of capture the flag. We will not tell you anything other than that it's connected and it's working. Frequency converter will be started in a mode that's simulating real work. So it will really report you parameters, it will report you current voltage, input, output, frequency, etc. There's nothing connected, like there's no real load connected to it for obvious reasons. And that's it. You just need to access it, and that means that you need to figure out how and where is it connected, and to figure out the protocol. So, okay, protocol is open source. You know which one it is. It's Modbus. There is some change in this protocol, which you will have to figure out yourself, and that's all. This is the simpler one. The more difficult challenge is the second one, where we took a micro version of our solution. So there will be a green box with our hardware connected to another frequency converter, also on Modbus. The premise is the following. You do not have physical access to either hardware systems. But you have access via, in first case, you have already SSH access. In second, you will just be on the same network. We configured it the way that, in the second case, data is sent over public IP, so we didn't close it in a VPN. So you should be able to sniff out traffic between the box and our sandbox server. And do what you can. So try to access the box, try to fuck up the frequency converter. If someone does that, I don't know, protect from others that are trying to do the same thing, and that's it. The server to which it connects is sandboxed, so it's a separate server from our normal dev environments or production. So do what you will, and you're supposed to write a detailed report what you did, what worked, what didn't work, what exploit you found, what you didn't find, and we will evaluate it with Tony, and that's it.
You'll get some ether for it.
Sorry?
Some ether.
Yes. So that's it. I don't think there's anything else to describe. I will not tell you the details on the protocol, but as I said, it's we set it on a public IP. There's no encryption, and you'll just have to figure it out. So it will run our normal firmware, or maybe some older version, but it's more or less the same as the production one, and that's it. There are some holes. I see Dan wrote holes. Yeah, so there are some deliberate holes, a few of them, I think 2, maybe 3, which you should be able to find, at least when accessing the box. But we'll leave that to you. And that's it. Any questions?
So just one statement. Mario is downstairs. He'll help you wiring everything up to the network. We will have a dedicated set of IP addresses, which we will write in a Google Doc file. So today we're going to set up all the arenas like ICS and drones. And you will have on the main page of the school, you will have a link to the targets document where you will see this IP is this IP is this IP is this. And so you can see that you're not doing anything on a system that you shouldn't be doing. Okay? So don't end up the entire /16 range. Wait for us to give you the IP addresses and target specifications. Okay? Sure. Questions? Not for me, for him.
Well, kind of a question for both, I guess, related to the network itself. So we're attacking devices that are on a segment of the faculty network.
Yes.
So I assume there are certain securities in place as part of the faculty network.
Is the Pope a Catholic? I mean, yes. So, one interesting point. If you're connected to FSEC hack 2018 with the password of hack all the things together without spaces, we are all in a /16 segment. And from that segment, you can reach the frequency converters, the drones, everything. This was by design. So you can be sitting here, connected to and then you can hack and do stuff. So you don't have to sit in a room
there any redundancy systems in them? And most systems that work 24/7 have a second backup, like system that will kick in if this one fails at any point. Is there such a thing installed?
It totally depends on the facility. So, for example, in more critical places like Pliva or something, there is redundancy, which is usually just another device which kicks in. But device itself usually doesn't have, like in the car, where you have double CPU, double everything on a single motherboard. They usually don't have that on PLCs.
So if there is a latency when one system crashes, that it can
Yeah.
the other to kick in.
Yeah. Yeah.
Questions? Any more questions?
You mentioned that some systems work for 10 years. What's the mean time of life expectancy?
No idea. But I know that it just, when I said 10 years, I didn't mean that the same piece of hardware is working for 10 years. It usually goes to shit much sooner. But they just buy the same model again and put it in. Sometimes it depends on the actual piece of hardware, but you can see them downstairs in person. They're nothing smart. They literally have pins where you pull in, put in plugs. And often anyone can replace them. So sometimes they have just replacement units which they switch and then someone checks it. And also like about this downtime, you know, if a sawmill stops for a minute or 5, no one cares, you know, it's not, it's also critical. But downtime of 5 days for any system like that is critical.
Any other questions? Then thank you very much.
Thank you.